Welcome to demonstration video 1 for ST2, our portion on hypothesis testing. So what we're going to talk about next in this is how to do normal distribution testing and z-tests with R, how to do one sample, two sample, and paired t-tests with R as well, and then also how to look at sensitivity and specificity in R. In the second lab, we'll look at power effect sizes and then also multiple test correction. So what we're thinking about with normal distributions is the idealized situation where we have a perfectly normal distribution and we can predict features about this collection of samples based on this distribution. But we also have to consider the reality that our underlying data might be more heterogeneous than this. And as always, what we want to do is kind of plot this data and understand it better. So what we have to think about with our data is to plot it and think about what features it have and whether we can actually apply parametric statistics to it, or if we can transform it in some way to understand it better. We have this central idea that if we have, say, some particular value like mini mouse here, and this mouse can run 10 meters in 12.4 seconds, and we can compare that against our reference population, whose mean is 11.6, we can look at that difference between that value of 11.6 against the standard deviation. If we have all these this population of mice, the entire population of mice, we can use the z-score as a way of scaling those differences. So our z value in this case lies out here. So this might correspond to our value of 12.4. And then this value in the middle is the mean. So that's our value of 11.6. And we're measuring the extent to which this value of 12.4 is different from the 11.6 value using units of the standard deviation. And here, this is 2 standard deviations away. So that corresponds to a p-value or area under the curve of 0.023, which is the area out here. And we can do that pretty easily with RStudio. What's worth noting here is that we can really think of these p-values as the percentile, showing how extreme this value is, because we have to consider that if we're applying a p-value, is that we're assuming that the null hypothesis is true for these particular values, that the hypothesis is well designed in the context of that experiment, that the model that we're using is appropriate, which is that our data is normally distributed here. And then in that context, we're testing how extreme our value is relative to the reference distribution, assuming that that sample could be a member of that distribution. So the p-value that we get here can be a function of all these different things. So note also, as I mentioned in the other videos, that the p-value is not the probability of something having a true effect or a no true effect or random chance. It is a mosaic of these 3 different things. That's why, as mentioned previously, we don't want to use this S word when we're talking about p-values. We can really think about these more critically and carefully, and think about the heterogeneity that we have in our data. So what's worth noting in our data as well, that if we have the underlying data that has a particular distribution, which might be skewed most commonly for biological data, occasionally uniform or just irregular, we can have a z-score for comparing the data in the context of these distributions if they're normal. But if we take the sample distributions of the sample mean, even if our distribution is irregular, the mean value will be somewhere in the middle. And as we get our increased sample size going from n equals 3 to n equals 5 to n equals 10 to n equals 20, we'll find that our approximation of the true population mean here in the middle, mu, based on our samples with that have a mean of x bar, will get better. So if we do a bunch of different samples, all of which are just taking sample means derived from 3 samples, we'll find that our approximation of the population mean is quite poor. But if we have sample sizes of n equals 20 and repeat that process where we get a bunch of sample means, our approximation of the true population mean will be a bit better. So those sample sizes will give, each of those will give a more accurate estimate of the true population mean, and also their aggregated shape will also give a better approximation of the true population mean. And in that context, we can say it's better because the level of uncertainty is lower. In that vein, it's also worth considering for these tests how many samples you might need to have a good idea of the sample mean, standard deviation, and standard error of the mean. I talked about this previously. So what we're going to think about then is looking at data that conforms to a normal distribution using the function RNorm. So we're going to switch to RStudio next and think about that further. So if you'd open up the hypothesis testing RMD file, in this lab, we're going to look at a few different points, and then we're going to look at firstly how to generate random numbers. So if we run this function RNorm, and we look at help from it, what we can find is that there's most of the functions related to it, like dnorm, pnorm, which gets qnorm and ornorm, that produce vectors of probabilities, quantiles, and numbers. So if we run ornorm, say we do ornorm for the example above, we are looking at getting 100 samples, given a mean of 3 and a standard deviation of 1.5. We can see is prompted by R down there. So if you type that in and press enter, we'll get a bunch of different numbers. And each time we run this command, we'll find that the numbers are different. So they're not the exact same. They're randomly generated with those features. If we change the mean to around 0, we'll see that the values are approximately around 0 each time. And if we make the standard deviation very, very small, 0.1, we'll see that they're all very, very close to 0. If we make the standard deviation much, much bigger, around 10, you'll see that they're much more heterogeneous. What we can do then is when we look at some set of values D, is that we can get a 5-number summary to see what the features of D are. So that's going from the minimum 0.021, the 25th percentile 2.18, the median 3.06, the 75th percentile 3.85, and then the maximum value 6.74. If we get the summary, we'll get the same bunch of different numbers, except we get the mean as well here. So that kind of matches our distribution of being 3 plus or minus 1.5. We can also get the standard deviation with the function SD, and we can see that as well. A good idea with our data is to plot it. So if we plot it like this, we just simply plot D. We'll see that it's not very sorted. So what can be good is to sort D with this command sort D. And then we can plot it, and we can see the sorted values of D, or the simple index of numbers is given on the x-axis, and we can add a grid as well if we want, and even change the point shape if we want to. So that's a triangle, and this one is a plus, and we can add colors if we want to. A more useful function in this instance might be a histogram, and we can write a function then hist with D as the input there. We can leave the color blue if we want, and leave the grid if we want, and that will give us our histogram here. What we can toggle then is the number of breakpoints we want. So we might have very few, like 5, which is the same as we have here, or increase that to 15. So that gives us some more resolved values as we go through. Obviously, we can take that to extremes that where we have too many breakpoints as well. So there's sort of a balance to understand fully what the features of our data are. So a way of testing if our data is normal is that we can use the Shapiro-Wilk test. So if we apply this to our data D here, we'll see that the p-value is large, suggesting that it is not different from a normal distribution. If we test that further, so in this instance, what we're going to do is create a new bunch of a new vector called D2, and we're going to concatenate onto this distribution our bundle of values. We're going to add on 10, 11, and 12 onto this distribution. We can then apply this to the Shapiro-Wilk test and see if that conforms to a normal distribution. So you can see here now it does not. And if we plot D2 again in the same way, we can look at the extent to which it matches a normal distribution. So you can see here we have those outlier values, which suggest this distribution is more skewed. If we give it a distribution that is less extreme, you can still see that we still get a small p-value suggesting it's not consistent with the normal distribution. If we have one outlier sample, you can see there the p-value gets more large as it moves towards a normal distribution. So that's a way of testing if our data is actually normally distributed. We can use the function p-norm as well. So this is this distribution function looks at the probability of x with a mean 3 and standard deviation of 1.5. So p-norm will give us the chance of observing this particular value in the context of this distribution. And as we move away from the mean, so let's say we have 0.5 here, we'll find that the p-value, the probability of this becomes smaller and smaller. We can go into negative values as well. And if we go closer to the mean, we find that that probability becomes larger. And that's of observing the area under the curve more extreme that value, to the left of that value, from minus infinity up to that value, which means that if we have a value on the right-hand side, like 4, we'll get a p-value that exceeds 0.5, which suggests it's on the right-hand side. So therefore, to interpret that p-value, we need to take the value of 1 minus p-norm. So that gives us the area that's more extreme than our observed value. So if let's say we have a value 6, we can see that our p-value, area 2, that's more extreme than this value, it's going from 6 to plus infinity, is going to be 0.023. And if you want the two-tailed p-value corresponding, let's say we have a new value and we don't know in advance if it might be bigger or smaller, we can multiply this again and get our two-tailed p-value and find that the value, how extreme that value is under that more balanced situation where we don't know if it's smaller or larger, and therefore you get the area under the curve on either side corresponding to where it's more extreme. That's going to correspond to 0.023 on either side. So that's the two-tailed p-value there. So that's important. So the examples are going to show other illustrations of that. It's important that for nearly all tests that we're dealing with, we'll be reporting the two-tailed p-value. And we're going to look at an example here where you have protein X that is normally distributed with a mean of 166 micromolar with a standard deviation of 12. You have a new protein at a level of 182, and you want to see how similar it is to this reference population. So we apply p-norm here. We can see that this value is on the right-hand side of this distribution, and we can use our norm. Let's say we want to simulate 1,000 values with a mean of 182. Oh, wait, the mean, this is incorrect. 166 and 12, and we're testing 182. We can simulate those values using our norm to create a data set we'll call it T3. And we can plot this to visualize what we're looking at. So if we look at a histogram of D3, which I'll just make some space for, you can see there that our value of 200, if we plot it on this distribution, or sorry, value 182 and the reference point of 166, is going to be to the right-hand side. So we're trying to get the area under the curve that's more extreme than this value. So what we're going to get then is we're going to look at getting p-norm. 182 is a query, mean is 166, and our standard deviation is 12 in the question. And that gives us the area going from minus infinity up to that value of 182. So therefore, what we need here is 1 minus p-norm. That's the one-tailed p-value, and the two-tailed p-value is going to be that multiplied by 2. So you just multiply that by 2 because the distribution is symmetrical on each side. So that's a two-tailed p-value. So we can do the same if we have other queries as well. If we have 155, that's going to be at the left-hand side of this distribution. So we don't need 1 minus p norm. So we get 155. That's our two-tailed p-value. 178 is on the other side of the distribution. So therefore we get 1 minus p norm. If we forgot to get 1 minus p norm for that value, we find that our p-value is greater than our two-tailed p-value is greater than 1, which is impossible. So if you get a two-tailed p-value that's greater than 1, obviously you've made a mistake somewhere. So that kind of gives an indication of how we can calculate standard normal distribution metrics using RStudio. So we'll move on now to looking at t-tests.